Okay, after the last week lesson about the number systems, today we have to discuss about this logic gates lesson. Actually, what are these logic gates? Logic gates are actually how this starting from the transistor, starting from a basic switch-based circuit to transistor to IC, VLSI, LSI, or large-scale integration circuits, integrated circuits, large-scale integrated circuits, then very large-scale integrated circuits, how these circuits are behaving, what is their logical behavior. So we are going to explain using these logic gates. One more thing. So if you think about your arithmetic and logical unit inside the, if you just take just ALU, arithmetical logical unit, which is inside the processor, control unit, which is inside the processor, random access memory or main memory, and then dynamic random access memory, cache memory, registers, how these things are constructed. These are all electronic circuits, how these are constructed, what is the logic behind this is called logic gates. So let's study very small circuit, how it behaves, and then we can move to much like complex logic circuits. So basically there are only three logic circuits, but using the three logic circuits, it is possible to construct more logic circuits. So let me start by introducing a switch, which is going to be a very small, there is no logic actually, but so this is the simplest version of control like circuit, which can be which has an input and output. So you can see the bulb can be considered as the output. Then there's a battery can be considered as an input, or the power source, or the switch can be considered as input. When input is given, you can see the bulb works. When switch on, the bulb works. When you turn on the switch, bulb works. Here, on in the switch will turn in on the bulb. So you have control over this output. Output can be controlled using this input. So this is the basic for any logic. Output can be controlled by using the input. That is the basic logic behavior. So where you can control the output of something using an input. This is how the keyboard. This is the keyboard actually. In our computer, this is like keyboard. This is the monitor. No big processing power needed because just pressing the key will turn on the bulb. It's very simple logic. That is it, not even a logic, right? So then let's make it bit complex. I'm going to have one bulb. Now two switches. Right? Two switches connected serially. And then the battery. Okay, let's name these switches as A and B. This is switch A. This is switch B. Okay, if these are switches, A and B are switches or inputs, how can we light up the bulb? Yes, what is the logic? How can we turn on the light? So here, if you close A switch, bulb will not work. If you close B switch, the bulb will not work. So what we can do? Yes?
Close two switches.
Yes, you can close both circuits. You can close both circuits. A and B, both can be closed. Then you can see the bulb is working. A and B, both can be closed. So the bulb is working. So that is what happened to the bulb. A and B both closed, then the bulb will work. So this is one logic. This logic is called AND logic. In AND logic, we have, if we combine any number of inputs, minimum 2, but even it can be 3, if you combine any number of inputs using serially connected switches, in order to, like now you have A, B, C, 3, All are serially connected, one after another. Now, if you need to turn on the bulb, you need to close A, B, C, all three. You need to close A, B, C, all three. That is the nature, right? A, B, C, all three. That is called AND logic. AND logic is where the serially connected switches or inputs, you need all inputs to be 1 in order to make output 1. Convert all inputs to 1, then output is 1. That is the logic of AND gate. If all inputs are 1, output is 1. So please remember that. That is easy to remember. If all inputs are 1, then output is 1. Right? That is the basic logic of AND. Then the next thing. So let's connect these switches parallelly without serial connection. I just need to turn on the switches parallelly. A, then B, just make them parallel. And you can add C also, but for the moment, let's omit that. A and B are enough. Okay, so then let's connect a wire from here to here. You can see it will start working because this A switch is turned on. If B is turned on, still this is completed, so it will work. If A, B both closed, still it will work. But if A and B both open, this will not work. So in the parallel connection, what we need to understand? In the parallel connection, we need to understand that if inputs are given, if inputs are given parallelly, or inputs are given, if one of these input is present, the output will be there. One of the input will generate the output. Minimum one is enough. If none is true, then the output is false. The previous one, all need to be true, or all need to be present to generate the output. This one, all of these need to be absent in order to not generate the output. So this is called OR logic. Or you can say either way, at least if there's a 1, the output is 1. If at least one input is, this is called one state 1, right? Because two states are there, no, off state can be called 0. Off state can be called 0, on state can be called 1. If input is 1, one of the input is 1, the output is 1. So that is OR logic. Or if all the inputs are 0, output is 0. That is OR logic. The other way, AND logic, if all the inputs are 1, the output is 1. If all the inputs are 1, the output is 1. That is AND logic. Okay, then when input is 1, output is 1, input is 0, output is 0, that is the normal, that is not logic. But if it is reverse, that is called not logic. If input is 1, the output will be 0. It's like a trip switch. When current goes, trip switch turn off. When current not goes, it will turn on. The other reverse. When input is 1, the output is 0. When input is 0, output is 1. Right? That can be considered as. So you have to use resistors and transistor to create that circuit. Here I don't have any transistors, therefore I'll skip that part and just go to the slides. Okay, AND gate or the AND logic. When all inputs are 1, output is 1. So this is actually explained using dot, the AND operation, A dot B. Right? Sometimes we can omit and we can write A dot B as AND gate. Right? This is the first logic that we have discussed. So in X and Y are inputs. If both are 1, the output is 1, otherwise 0. If both are 1, the output is 1, the otherwise 0. And or logic, if both are 0, output is 0, otherwise 1. That is all logic, and this is the gate, and we denote that using plus. Actually, this is called boolean algebra. The boolean algebra, boolean A or B, A plus B. This is called boolean algebra. Right? So, shall we write down the table other way? Like this table has a problem. I just downloaded because I kept the notes at home when I come here. So please start from please, when you're drawing the truth table, please draw like this, right? A, B, then A and B. You can say both are 0. This is 0. 0, 1 is also 0. 1, 0 is also 0. 1, 1 is 1. When drawing the truth table, please write this way, right? First, so write down the main heading in logic gates. Write down the logic gates, heading as the logic gates. No need to write down this part. First write down AND gate, and then draw the symbol. So excluding this, right? This truth table need to be replaced by the table given here. Other than that, other things can be written. So don't write the NAND gate, right? Only write about AND gate. Do not write about NAND gate, right? Only write about. This is the truth table, A and B. Quickly AND gate, then write down the statement. If all inputs are high, output will be high. Draw the symbol. Write down this special purple color box statement in the purple color, and this is called truth table. Truth table. Satyatavadu. Truth table. So please write down. Let me know once you're done. Okay, this is the circuit explanation. So you can see the switches are serially connected, and so this can be explained this way also. There is a tank and there is a water pump. It has two switches, serially connected switches. In order to get water from this end, you need to open both valves. Both valves need to be open in order to get water. That is similar to the bulb will work if both switches are closed. Similarly, if both valves are open, water will come. So that is the idea. That means if any number of inputs are there, doesn't matter how many number of inputs are there. If all are one only, this will be one. That is the idea. Just draw these two and also this one. Then please write down this. And also write down if both valves are open, then water will come. So OR gate is basically how it works. OR gate will work like this. If both are or all inputs are 0, the output is 0, and this is the way. And you can see this. You have to read that this as O. Don't read as A plus B. Read it as A O B, because this is logic, right? You can write this: one or more inputs high, then output will be high. Or the other way, if all inputs are 0, output will be 0. Both are valid statements. But when you are drawing the truth table, as I said earlier, draw the other way. I'm not agreeing with this, like this is okay, this is correct, but basically you better write like this: X O Y. So because this is we have to start from the lower number, and 0, 1 is 1, and 1, 0 is also 1, and 1 or 1 is also. So please draw the truth table like this, because don't draw this one. Instead of that, please draw this one, starting from the lower number to the higher number. That is better way of showing this. Please draw the truth table also. Explanation can be added to the same thing like this. Let me erase this or to the. Okay, the logic explanation is this. Here you can see the parallelly connected two switches and the bulb. He also parallelly connected valves and the pipe. So in order to get water, you can open either this one or both. Water will come, but if both are closed, water will not come. That is the nature now. Here also, if both are open, the bulb will not work. But one of these or both are closed, the bulb will work. Right? That is the nature. Right? Then you can explain the same situation like this. If both switches are open, then the both switches are open, switch off, the bulb will not turn on. Right? And so what is the logic explanation there? You can say if all inputs are 0, the output will be 0. This statement was not there in the previous one. They have just mentioned if either input, but just write down this statement too. Similarly, please draw this one and also this one, then write down this one and also write down these two statements. The last one is the simplest one, that is the NOT gate. There's nothing actually you need to do about that. Basically, it will invert the output. When input is given as 0, the output will be 1. When input is given as 1, the output will be 0. So that is the third one, not logic. You can just write down this and also the truth table and also the symbol of NOT gate. NOT will invert the input. Sorry, it's not the output. Not will invert the input and produce the output. Not will invert the input and produce the output. Please write down NOT gate, symbol, truth table, statement. Okay. Then, so the next subheading is combinational gates. Combinational gates means how we can combine them together. Once you written down that part, focus on this. There is a OR gate, that is A or B, present in A or B as the output. That is then sent via NOT gate. Then A or B will be inverted. Not inverting can be done like A inverted like A dash, A hyphen like the A dash like this, or A bar. A bar is also acceptable. Yes, this is another way of telling. A bar means you can draw a line top of the A. That is A bar or A dash. This one angle dash or this one will work. Both are representing NOT. Okay, then combinational logic gates, and please draw this one. Try to complete the following truth table. This truth table, try to complete that according to this. Okay, if you can send it to into WhatsApp after doing, then I can review. Draw this, then try to complete the truth table. Right. Okay. So the combinational logic is when combining the gates. Right. You can see. So this is when 0, 0 gives 0. Oh, check. This is OR gate, right? OR gate will give only that you missed. Both are 0. OR gate will give 0. This is OR gate, not AND gate. Both are 0, OR gate will give 0. This is OR gate. A, O, B, no. A and B, no, I keep it high. Both are 0, this is 0, otherwise it's 1. Then the reverse will be 1. And you are writing that as a different gate, that is called no gate. Okay, now you can complete that too. Because mistakenly you have written the other way. Understood? There. Because
Yes, sir.
OR gate the logic. If both are 0, it is 0.
Yeah.
Because there are like, these are closing, these are like going closely. So in the examination, 1 bit error even give you a big error. Therefore, be careful when you write answers. Okay. So try this one now. This is my ugly drawing. Don't worry for much about that. This is A, B. This is, what is this gate? This is AND gate. Right? A, B. This is AND gate. Now I'm sending that to a NOT gate. Now try this one quickly. That is the previous one that you have seen, right? The previous truth table. This is called NAND gate. Here.
Actually, sir, I draw the two gates actually. I also draw the NAND gate and NOR gate.
No, NAND gate, no gate. Okay. Right. This is NAND gate. NAND gate is the truth table for NAND gate is this one, right?
Yeah.
Okay. Then, so there's another way. You can not this first. A can be noted, B can be noted. Then you can send it to the OR gate. Actually, this is called inverter OR gate. First you invert, then you OR. Inverter OR gate. Right. I need you to draw this and also inverter AND gate. Try both inverter OR gate and inverter AND gate. Also the truth tables. Right. Just using that logic, we can prove one law that we are going to learn. That is called De Morgan's law. Actually, what De Morgan said that if you take A and B, then not it. A and B not it. That means NAND. Can you remember the NAND gate here? 1 1 1 0. 1 1 1 0 is the result of NAND. That result is equal to A naught O B naught here. 1 1 1 0. This is also 1 1 1 0. The last result, right? Not in the intermediate result. So compare this. This is 1 1 1 0. This is also 1 1 1 0. What De Morgan said, this is A naught, B naught. Separately you OR it. That means this is inverter O. Inverter O is equal to NAND. Actually, how he explained that, he was telling that A and B, the common knot, you can distribute among A and B as individual knots. Now it is A naught. Now this is B naught. And intermediate symbol need to be changed. Here actually dot need to be changed to plus. That is what De Morgan said. And similarly, you can say So this is the second format. A, O, B, everything not, the common not can be distributed to A and B individually, and the middle symbol can be changed. Okay, so you can write the first format and second format of De Morgan's law there. The first format and the second format. Actually, using this, you can prove this. The first format and second format, you can prove using De Morgan's law. Prove De Morgan's law using these two circuits. Sorry, these two circuits. We will learn more laws in future, right? It's only the start.
Okay, sir.
Right. Okay. Here I have given I have given one thing. So please write down this as a question. Draw a logic circuit for the following truth table. Use AND gate, OR gates, and NOT gates only. Right? Use AND gate, OR gate, and NOT gates only. Okay, this is the circuit. You're going to draw a logic circuit for the given truth table. You have to use OR gate, AND gate, and NOT gate only. Let's start that now. Right. What you have done is correct. Using this, you can generate. But so let me suggest you easy way of doing this. Just see them. I just wrote in front of here. There is a 1. In order to obtain 1, I need to not this no A not, but B is originally 1. No. A not and B will be 1 for this case. For this case, A and B not will be 1. For sure, it is 1. Because you know the nature of AND gate. If both are 1, then that will be 1. Here, both are 1 when A not is 1. Here, both are 1 when B not is 1. So, if you OR them together like this, if you OR them together like this, that will create that gate. So, that is the magic. Right? Okay, I hope this is clear now. Okay. So, see, A not B, then this one is A, B not. Drag little font. Actually, when I add this to the Google Sheet, it changed some parts. That is the reason why I cannot see that properly. Because when I added this to the Google, it has changed when I add this to the Google Docs. That's the reason why you cannot see this properly. Anyway, just get the idea. Don't think much about the drawing, because I just used word for drawing. That is not really accurate. Here also we can see. So just think about the gates, and this is easy way of doing the same. When you draw the circuit, can you see? When you draw this, you will get this output. The first gate will produce this. The second will produce this. If you owe them together from the first one and the second one, you can get the output. Whatever you have done is also correct. You generated this one, and then AND them together. That is also correct. Okay, just have a snapshot and draw in the. Right, next day I'll be discussing more about this logic gate and Boolean algebra, and especially about this Boolean algebra laws. Okay, then good night.
Good night, sir.